So, just briefly, then, what is the Big Bang Theory all about? It's got something to do with these words here, um, and in general, Big Bang Theory states, and we probably already know this, that the universe expanded. It started out as a point in space. Oh, no, not a point in space. A point where space itself was contained. Now that concept is a bit weird to understand. When people say what did the universe expand into? There was nothing to expand into in the first place. It was everything. So it's like dimensions themselves, space itself, the space in which the stars now exist, that expanded as well as the stars themselves. Um, we're going to look into some of these things. The redshift is connected to the Doppler effect. The CMBR is connected to the redshift. So to help us to understand how, one second. Okay, so let's to help us to understand how the universe could be expanding and how that might be experienced by somebody in this expanding universe. I'm going to draw a grid, and we're going to draw two grids exactly the same size, one over the top of the other. The first grid will represent the universe at one point in time, and then the second grid will then expand, so you'll be able to compare the how big the universe is compared with how big it was. So I'll just pause the video and make that now. Okay, so we've got what seems like one grid, but if I expand that one grid, we can see that actually there's a grid behind it. That black grid behind it represents its original size, and the grid just represents, a sort of units of distance from one point to another. What we're going to do is we're going to put on points of references, and we're going to see how those points are experienced from each other. So you can imagine being at those different points and how other points in space seem to behave in comparison. I'll show you. I'm just going to label those points with text. So we'll label them as A, B, C, and D. So we've got a few different points here in this universe. Now, bear in mind this universe is 2 dimensions. Ours are 3. Well, actually more than 3, but I won't go into that right now. But 3 spatial dimensions that we experience. Everything we experience is in 3D. You can have 3 different dimensions. Let's briefly recap. What does that mean? If something has 2 dimensions, well, if I'm able to draw a straight line at all, that's not straight. Let's just change that. Then I have at least 1 dimension. And if I'm able to draw a second line that is perpendicular to that first line, then we live in at least 2 dimensions. And if I'm able to draw a third line that is perpendicular to both of those, I live in 3 dimensions. Now, as you can see, I can't do that here because I'm teaching this lesson on a 2-dimensional surface. And so there's no way that I can draw this third line that's perpendicular to both of them. But if in 3D space, what you can do is you can point your finger on the screen at the center of this cross here, and your finger will be perpendicular to both of those lines, and that'll be your third line there. So we have to go at representing 3D shapes by drawing cubes like this on a 2-dimensional surface, but they're only representations of the actual object, and in actual fact, you can clearly see. I mean, that's a right angle, that's a right angle, but that isn't a right angle, is it? We make this presumption that it's some sort of using perspective. That's how we would look. That's how we would see a cube if we were looking at it like that. So you can't draw. But I don't want to go off on too much of a tangent, but that's just a little bit of recap about dimensions. And this universe is only in 2 dimensions because it's going to be basically impossible to show how it works in 3 dimensions at this point. So what we're going to say is that the distance between any 2 lines like this, we can just call, let's just say it's 1 meter, as it's a very small universe, and yeah, so the distance is going to be 1 meter is a division like that. Now, yeah, well, that's right, and you say that it's a very small universe, isn't it? But then our universe used to be very small. In fact, a lot smaller than what we can see right here. So we're going to actually start off by doubling this universe and doubling it in terms of its dimensions, not in terms of its area. So and remember, and again, coming back to dimensions, area is just a two-dimensional version of volume, or volume is a three-dimensional version of area, isn't it? So we're going to double, but we're going to just double the dimensions. So what? How would I know if I double the dimensions? If I increase this, eventually we're going to get to a point where the each square is going to have actually 4 squares in it, because each dimension will have 4 of these in it. So looking back on this, I probably should have actually made this black grid a lot longer, a lot larger, so as we can see it on these other stages. But you can sort of work it out because I've made it fairly simple. So now the distance between A and B was 1 meter, and now it's 2 meters. The distance between B and E was 1 meter, now it's 2 meters. So let's say that happened in the let's say that happened in 1 second. Then A would look at B and think, oh, B is moving at a speed of 1 meters per second. It would look at it and say it's moving away from me at 1 meter per second, and B would look at A and say it's moving away from me at 1 meters per second. Now, originally, let's look at C. In fact, C was originally 2 meters away, and now it's 4 meters away. So C's actually, from the point of view of A, C's actually 4 meters away. It's moved 2 meters in the same period of time. So when it looks at C, the velocity of C, A would measure it as 2 meters per second. And also C would measure A as moving 2 meters per second away. So 2 things we can see here is that everybody would experience everybody else as moving away from them, and might conclude wrongly that they are the center of the universe. Each person would conclude that potentially. And also what we can see is the further something is away from you, the faster it seems to be moving away from you. So if we look at D was originally 3 meters away. Now it's 6 meters away. So it's increased. It's increased by 3 meters. By 3 meters. Yes, exactly. So so the key thing to realize here is that not only is it that the things further away are moving away more quickly, but also that the velocity that something is moving, that's not a very good V, is it? The velocity that something is moving is directly proportional to the distance it is away from itself. Now, this is in 2 dimensions, but this would work the same in 3 dimensions, because I've singled out individual dimensions, haven't I? I'm not looking at how much the area has increased, but I'm looking at how much the distance has increased. I doubled the distance, and when I doubled the distance, obviously the distance between all the objects is doubled. But in terms of the change in the distance, that is directly proportional to the distance from the object, because it has just doubled, and if it increases if the rate at which it's increasing stays the same, then it's going to the velocity. Well, no, it doesn't actually. That doesn't matter. But if over that 1 second, it doubled, and so everything would have the seeming velocity of everything that's moving away from it would be directly proportional to the distance it started at from it. So that is something we notice when we look at the recessional velocities of galaxies. In other words, how quickly galaxies are moving away from us. So it would suggest that not only are the galaxies moving away, but that the universe itself is expanding.